and welcome to Unnatural Numbers, the YouTube channel where we try to find out what really is the biggest number out there. I'm Ben Cornish, and I once got a bronze medal at the UK Junior Maths Challenge, and I'm joined today with my fabulous guest, Paddy Moore, who is a maths teacher and quiz enthusiast, and Katie Steckles, who is a professional mathematician, author, and YouTube superstar. Welcome both.
Thanks. Thanks for having me.
I can definitely vouch for the fact that Paddy is a quiz enthusiast because he has already tried to recruit me for his quiz team
He has been
before
chatting
starting
us up.
recording. Yeah.
Yeah. First things first. Most important things, right?
So I know what you're both thinking. What's that for? Well, that's because that is the title of today's episode. We are looking at the number 4, which is the fourth natural number. And here we've got lots of facts about the number 4. Paddy, I think today we are going to be starting with you. What is your fact about the number 4?
My fact, Ben, is that 4 is the first square number.
Is it?
Yeah, it definitely is.
Is there not one before that?
Nope, it's not
Okay.
a square. I'm going to right. Okay. We'll this is carrying on an argument or a discussion from the first episode that I was on with Ben,
Right.
and I'll try and you feel free to argue the point, but we can definitely say that if I do 0 squared. 0 times 0, that's 0. That's not going to be a square. It's got no dots at all, right? Okay.
Oh, yeah, I
Yeah.
can't see any squares that you've drawn there.
Yeah, no
Yeah.
squares there. If I do
Right.
1 times 1, that'll be 1.
Yeah.
If I do 1 dot is not a square. It's a point. It only doesn't have 2 dimensions. It's one-dimensional. Can't be a square.
But is it not a square because you could put it in a square? Like you
But I
could
can
draw a
put-
little box around it and that box would be square. Whereas if you had 2 dots, you couldn't.
I can put 5 things in a square. If you're going to argue that, there's 5 things in a
Oh.
square. That's not a square, though, is it?
So I learned maths from a guy called Euclid, and he told me the number 1 is really just a length. And surely if I have that length of 1, that's then a square.
You can argue that, but my argument is based on dimensions, and this is 2-dimensional because we now have something that I can actually join up all 4 corners.
I will concede it's the first proper square.
That, I think, is the best that I can do, really. Yeah.
Yeah.
It's the first proper square. And I think it's a really interesting number just for that. But also, since we're talking about squares, did you know that every square number is congruent to either 0 or 1 in modulo 4?
What?
Every square, yeah, because they all end in specific things, right? They all end in
Exactly.
1, 4, 5, 6, or 9.
Yeah.
And I know that 'cause that's quite a useful thing when you're doing puzzles. But
that means that we can, but we can also just show. I can show you this.
Yeah, I guess mod
Quite
4
nice.
is slightly harder because then
Yeah, you'd need the last 2 digits for mod 4, wouldn't you?
Yeah.
Yeah. So I can show this algebraically, and the reason I want to do this is because this is like one of my favorite bits of maths is proof, and the fact that we can prove that things are always true for everything is absolutely like fundamental to maths, and it only happens in maths. You can prove that this works for every possible conceivable number, which I'm going to attempt to do algebraically now. Okay, nice simple bit of GCSE maths to help us here. Okay, so I'm going to try and prove this algebraically. I'm going to start with n, where n is some multiple of 4. It's just a number in the 4 times table.
Okay.
And then if I take n squared, that's equal to 16k squared, which can be written as 4 times 4k squared, which is obviously a multiple of 4. That means it's congruent to 0 in mod 4, which is nice.
Okay.
And now the next number up will be 4k plus 1. And if I square that, I am going to get 16k squared plus 8k plus 1, which I can rewrite as 4 times 4k squared plus 2k plus 1. And that is 1 more than a multiple of 4, which is nice. And I can carry on because we've got to do all the numbers to prove it. A proof by exhaustion requires us doing all numbers.
I was slightly intimidated by the concept of checking all the numbers, but actually that's only 4 different things because you've got things that are a multiple of 4, things that are 1 more than a multiple of 4, things that are 2 more than a multiple of 4, things that are
Things
3
that are
more than a
three
multiple
more
of
than a
4,
multiple of 4.
and then
Yeah.
things that are 4 more than a multiple of 4 are just a multiple of 4 again. So
Oh,
we'll be
you've
done. Yeah.
headed off my. I was
Yeah.
going to do every single
That
number.
will make things fun. So, yeah.
Yeah, I've saved you a
This
lot
was
of time here. Yeah.
so yeah. Okay, we won't do every single number, but we do need to do these next ones, and perhaps we can speed this up in the edit because that will be quite helpful if we can.
I'm interested because I was, your first one, you start with a multiple of 4 and the square is a multiple of 4. 1 more than a multiple of 4, the square is 1 more than. 2
Yeah,
more than,
is still
it's just a
multiple of 4.
multiple of 4. It's not going to be 2 more than. Yeah.
Yeah, because I mean,
Well, because 2 squared is 4, right?
right. So so if we say
Yeah,
3 squared is 9,
right. That's 1 more than a multiple of 4. So I've got a
and so
prediction for
you've
what's going to
already
happen with
spotted.
this, right?
Yeah, you've already spotted it.
Good, good.
So
Yeah.
16 squared plus 24k plus 9 is 4 times 4k squared plus 6k plus 2 plus another 1,
Yeah.
which is going to be congruent to 1 in mod 4. I love that proof.
Hmm.
And are we confident that all of these numbers here have to be integers?
If k is an integer,
Ah,
then
yeah, so
just
k is an
squaring it
integer.
and multiplying it by
Yeah.
things. Yeah.
Okay, so I think that probably means that I should go a little bit more detailed on what modulo 4 is.
Yeah, I feel like because you've said reasonably often 1 modulo 4 or 0
Yeah,
modulo 4, but it's kind of the same as the other thing that we're talking about here, which is 1 more than a multiple of 4 or the same as a multiple of 4.
yeah,
Like that's the idea behind it, isn't it?
it is.
I'm also
So,
interested in your use of the word congruent. I was hoping you could explain what you meant by
oh,
congruent.
I looked it up. It means the same size and shape, but I think
So
I might be
shapes.
looking in the wrong dictionary.
Yeah, that's
I
not
think
numbers, is it? That's shapes. Yeah.
no, I think that it's I think that congruent in this case means that it's equal to, but with the caveat that this is converting from base 10 into modulus 4. So the things are, you wouldn't say that 9 is equal to 1, you would say that they're congruent to the 1 in base 4, if
It's,
that's,
yeah, it's essentially the remainder if you divide by 4, right? If you've done divide something and get a quotient and a remainder.
yeah,
Like if you do
Hmm.
4 divided by 4, there's no remainder. If you do 5 divided by 4, it goes in once and there's remainder 1, and so on. So the numbers on the bottom there are kind of the remainders when you divide by 4 of the numbers at the top.
yeah, exactly.
Um, but that is how you convert to mod 4, I guess.
Yeah, that's it exactly. And mod arithmetic is actually used in a whole load of places. Clocks, when you're telling the time, you've just been working in mod 12, for example. Um, ISBN numbers on the back of your books. That's one way. Also, bank card details for data transmission. It is absolutely vital that you have some way of checking that the data has gone across properly, and so they use modulus arithmetic and different bases and algorithms in order to be able to confirm that they've actually sent the data correctly. This stuff's really actually useful in real life, which is disappointing, but
Yeah, sad. It's a sad thing, but I'll allow it. I think
yeah.
Applied number
yeah,
theory.
they're very useful in computing. There's a lot of computer uses for them, but they also there's a lot of mathematical use for them. Like it's
Oh,
just a really nice, useful concept that pops up in lots of different places.
yeah.
So, Katie, I think that's going to bring us over to you, and I'm very excited by this blank page ahead of us. Katie, what have you got today on the number 4?
Well, I was going to use a different page that's not even your page. So I have this page, which is an actual real page in front of me. And hopefully I will be able to write on this more easily than I can write with a mouse. So the thing that I would like the thing that basically jumped to mind for me when I was inspired by the number 4 was the idea of group theory. And this is, I guess, a whole branch of maths which if you've done a degree in maths, you'll have seen some of this at some point somehow. It's something that's definitely always covered in pretty much any maths degree at least once. But if you haven't, it kind of just it kind of makes sense of a lot of things for me. It's a very, very simple idea that mathematicians have managed to make incredibly complicated so that they can put it in a maths degree. But I think it's a really nice thing to think about and a nice sort of useful way of viewing the world, if that makes sense. And essentially a group is a collection of objects, right? This is the standard English meaning of the word, is it's a bunch of things. So we might have a set of objects, and in order for it to be a group, there's a couple of things that need to be true. So first of all, we need, I guess, a rule for combining two objects, and we can think of it as plus. So for example, if our objects are numbers, we can add numbers together. And the only thing we need this to do is that if I take two objects from the group and combine them using whatever my rule is for combining two objects, the thing that I get is also an object from the group. Right? And if you add together two numbers, as long as you do it right, you should end up with a number. And you can think of lots of different sort of systems that have this property. So like if I have two numbers, I can add them together. There are a whole bunch of different structures in maths that we play around with, that you can take two of them and combine them, mash them together somehow using some rule and get another one of those objects. And I guess you could have an infinite group. So if you have the group of numbers, well, we need to be more specific than that, and we need to spell the word infinite correctly. If you have an infinite group, writing and talking is really hard. An infinite group could be something like all whole numbers, right? So one of the notations we use for that is Z. This is just all of the integers. And if you take some integers and add them together, you always get more integers. And there's a few more conditions on the sort of definition of this operation that we need that kind of make it behave nicely. So it's things like if you add together two numbers and then you add a third number, it's the same as if you added the second two first and then put the first one on the front. And, things that kind of make it make sense and make it behave well and play nicely. And it turns out these structures pop up all over the place. So you can also have finite groups. And these are my favorite types of groups, and that is because they're small enough that you can kind of look at them and see the whole thing, right? The infinite group of whole numbers, there's a lot going on there. A finite group, we can just look at all of the things in it and see how they behave together. So for example, there is a group that contains three things, and it is sometimes called Z3. Because the three things that it contains are whole numbers from Z, from the integers. But it is, I guess it's the set containing, let's say, 0, 1, and 2. And the operation that we use here, and I'm going to horrifically abuse notation and say that plus equals addition. I'm going to put some quotes around that equals addition mod 3. So exactly the thing we've just been talking about, modular arithmetic. If I take two objects from this collection of objects and I add them together modulo 3, I will always get something from this set, because the mod thing means that we're always just taking the remainder. So if I add 2 plus 2 and get 4, that is 1 mod 3. So this object of the group, if I add another one of that to it, I get the second object. So this is now this sort of nice little self-contained ecosystem, and this is a group of order 3. And in fact, this is the group of order 3. There is only one group of order 3 in existence, and it is this. And the really fun thing is that there are just lots of different ways of writing this down. So for example, if I have the cube root of 1, this is a number, and if I multiply it by itself, I get what I guess you would call it the cube root of 1 squared. So that's the notation for this. You could write 1 to the 2/3 if you're using that kind of notation. And then if I multiply that again by the cube root of 1, so cube root of 1 squared times cube root of 1, I just get 1. And this has the exact same structure as this little group here, because I've got an object which in this, I guess, corresponds to the 1, which is this thing. And if I add it to itself, I get the 2. And if I add another one to that, I get back to the 0. But they behave in exactly the same way, except now instead of plus being addition mod 3, it's multiplication. And I'm multiplying together the roots of unity, the cube roots of unity specifically. And this same structure crops up in lots of different places. If you're thinking about, so another nice object that you have in mathematics is a permutation, which is when you reorder some things. And I might have a permutation that takes 3 objects and swaps them all around in a little cycle like that. It takes this object and moves it to there, this object and moves it to there, and this object moves it to there. And say that these objects are called, A, B, and C. I could apply this permutation again, which is now my operation. It's doing a thing again. And I would end up with the same set of 3 things kind of shifted around one. So now I've got A over here and B over here and C over here. And it's another thing that if I repeat this again, I'll get back to where I started, right? When I states in the same way that I'm moving around between these each time I add 1. And if I combine any of them intermediately, if I say 2 times 2, that's the same as doing the one where I shift it around twice. So I shift it around 4 times, which is the same as shifting it around once. So this is all the same kind of object. And as far as a group theorist would be concerned, these are all Z3, right? These are all just this same group. And the reason why I like the number 4 and why the number 4 was exciting to me is that we have got groups of order 4 and they're better, I think. So if we start simple and we go Z1, Z1 is just a group of 1 object. It's the boringest group of all time. Z2 is the group containing 0 and 1, again with addition mod 2. And this is, I guess, a reasonably boring group, but it comes up quite a lot in computing because we use binary numbers and they just have 0s and 1s. And so you end up playing around with structures that look a bit like this. And there is only one group of order 1, only one group of order 2, and only one group of order 3. When you get to 4, there are 2 different groups you can have. And this is when things start to get interesting. So we can have Z4. This is a perfectly reasonable thing to expect. So we have 0, 1, 2, and 3, and we do addition mod 4. And we have this same sort of structure. And we sometimes call these a cyclic group for reasons that potentially might be apparent when you think about what kind of structure we've got there. We've got things that cycle around. Do you have a question, Paddy? You look like you have a question.
No, I am trying to think what the other group is. I'm playing guess what the next group is.
Wow.
And I'm thinking about multiples, which I suspect is a little bit too simple, but I'm wondering how this is going to work. It's looking really interesting.
Okay, well, this is the group of 4 things, and we add them together, and they kind of go around in a little cycle. And if we do 1 plus 3, that's 0, and if we do 2 plus 2, again, that's 0. Like these all kind of loop around.
Are we limited to Zs, or can we play with other things other than Zs?
I mean, we don't have to call it a Z. You can call it whatever you want. This has got the same structure as 4th roots of unity and permutations that cycle around 4 things. They're all kinds of different things. It can be expressed in terms of, I guess, integer, modular integer groups. But it is a thing called the Klein IV group.
Oh.
And Klein was a mathematician who did lots of interesting things. I'm not completely sure why this is named after him.
Is he the guy that did the bottle?
There is a bottle. I believe it's the same Klein, but I'm going to be honest, I haven't checked. I'm just assuming there's one Klein, but someone can correct me on that. Head to the comments. No. So this is sometimes denoted V, which is from the German for 4.
And from the Latin, not 4, but actually 5.
Yeah. I think that's much more confusing. The group is of order 5 yeah. Anyway, it's sometimes denoted V because it's the 4th group. You can call it, if you want to express it in terms of integers, you can call it Z2 cross Z2. I very carefully said cross here. I'm not multiplying together sets. That doesn't make sense. But it's essentially, if you've got 2 sets like this, you can cross them together. And what I mean by that is that I'm going to make a set where each element is 2 things, one from this and one from this. So this can contain 0, 0, 0, 1, 1, 0, and 1, 1.
So that's the unit square.
I mean, that's if you're treating them as coordinates, then yes. I'm treating them as pairs of numbers between 0 and 1. That's what they are for me.
Okay.
If I combine these using addition mod 2, then it has the structure of the Klein IV group. So if I take, for example, this one and add it to this one, I got 0 plus 1 in my first coordinate, so I get 1, and I've got 1 plus 0 in my second coordinate, so I get 1. So I get this guy.
Mm-hmm.
And the structure of this group is different to the structure of the cyclic group. So in the cyclic group, we kind of everything just sort of wraps around. This one, things go in different directions. And I guess another way of thinking about it is in terms of symmetries, right? So a cyclic group, we can think of as a group of rotations. So if we've got a thing, mod 4 like this, if we had something, a shape that, for example, like has little kind of flags on it like this, right? Then if I'm thinking about symmetries of that shape, I can rotate it around that center point and get the same shape back. And if I rotate it 4 times, I get back to where I started. If I rotate it 3 times and then rotate it a further 2 times, that's like rotating it 5 times, which is like rotating it 1 time because we're working modulo 4. The Klein IV group is the symmetry group of, I'm going to say the letter H. That's what it's the symmetry group of. And in this object, we now have reflections. So we have a reflection here and a reflection here. And we also have a 180-degree rotation.
Ooh.
And these are well, and we have not doing anything, which I'm going to call 0-degree rotation, which is the worst rotation. But
You
if
keep using best and worst. Does the worst rotation imply that there exists a best rotation?
yes, that one. I mean, they're the only 2 rotations in this universe now, so
Okay, that's
it's better
fair.
than that one, right? But yeah, these are the 4 elements of this group, and they combine in a slightly different way. So instead of having this thing where they all just kind of go around, these 2 sort of pair up because there's 2 reflections and 2 rotations. If I combine anything with the no rotation, then I just get that thing back. Which is in the same way as if I add anything to 0, I get the same thing back, because there's always that kind of structure going on in the group. But if I did both reflections, I get the rotation. And if I do a reflection and a rotation...
Okay, now I find that so much easier to work out using your group there, because I just added the reflection and the rotation together, and I got the other rotation, the reflection.
Yeah.
So that
Yeah,
works
so
really
these
nicely.
are exactly these. So this is rotation by 0, this is reflection 1, this is reflection 2, and this is rotation by 180.
Yeah,
And
and
that, like, there's it's
if
just
you
the
can
same
just add them
structure.
together, yeah.
Yeah, but
Sorry.
expressed in different ways. And like sometimes people like to call these, so we always have the nothingy element that doesn't do anything. And in this case, it's 0 because if you add 0, nothing happens. In this case, this one's 0 because it's not doing anything. But we sometimes call it E for identity element. I don't know why it's called E. It's
E
sometimes
for
called,
identity?
yeah. Welcome to maths.
Identity.
Yeah, E or 1, it's sometimes called. Because 1 is the identity for multiplication, but if you use 1, it's very confusing if you're not doing multiplication. So E is sort of like, don't look at me. And sometimes people would use A, B, and then AB as the 4 elements. And if you're going to define it this way, you kind of need to specify how these things interact with each other, because here we know that it's addition pairwise. Here we know that it's combination of symmetries. So what you would sometimes see is you'd see it written like this. The angle brackets mean that it's a generated set. It's the set that's generated by the elements A and B. So it's all the things that you can make by mashing together A's and B's in different combinations, such that A squared is B squared is the identity. And that is a way of writing the Klein IV group. Oh, and sorry, one other condition that I need is the same as AB all squared is the identity. So in this group, if I take A and multiply it by itself or combine it with itself using whatever my operation might happen to be, I know that AA is just the identity, BB is just the identity, AB is the identity, and that is enough to define the whole thing, because that means that this element exists, the identity exists, because I can make it by taking 2 A's, and the element AB exists because I can take one of each of these and multiply them together and get it, and nothing else can exist because if I take any of those three things and square it, I get back to the identity. So it describes the whole thing, but in a very notation-y kind of way.
You mentioned earlier that the groups had to have the property of associativity, or I think you said that it doesn't matter the order in which you apply the combinations. Is that also suggested by this notation, or is that obvious and I'm not seeing it?
It will be true. It's one of those things that can be slightly confusing because associativity is a very specific property. So if we have, for example, A times B, that's not necessarily the same as B times A. And that's one way that you could interpret it doesn't matter which way around you do it. That is not what we're talking about at all here. So that's a totally different property. And in groups, that often isn't the case, right? In numbers, it's the case, because if you add numbers, it doesn't matter which way around you do it. In groups, that suddenly becomes not a thing. And this is commutativity.
So that's commutativity, yeah. Whereas it doesn't matter whether you combine A with B or A with A with
so
B.
if we did, I mean, let's try it. So A times AB should be B, because that's the same as A times B.
Yeah.
And that's just the identity times B.
How do we know that they're associative, though? How do we know the result of A times B only to then be multiplied by A?
It's one of the definition. It's one of the rules required for something to be a group. So I guess.
So it's just sort of implied by it being a group. Okay.
Yeah, and this. I think if this wasn't a group, then we wouldn't be talking about it. Yes.
So to give some context to my question, when you were showing me the group, the Klein IV group, I was thinking that's the unit square. Then when you started talking about the modular arithmetic in mod 2 of the unit square, it made me think of the sort of topological connection of it, and it looks like it's a torus.
Yeah, because I guess if you go from if you wrap around, you go back to 0 again. Yeah.
Yeah, it's Pac-Man rules, isn't it?
Yeah.
Yeah. And I don't know if it's immediately obvious that movement on a torus is also associative. It doesn't feel like it should be.
I think it's because you come back to where you started. Like this, it's like your only option to be on the inside or the outside. There's no in between. So it's not quite the full motion on a torus. It's motion on a very strict subset of the torus where you're only allowed to do half a move at a time.
Right. So I'm thinking too continuously and not discretely.
Yeah. Okay. You can have continuous groups, but no, not finite.
And that brings us on today to my fact about the number 4. So for my fact, I'm going to be asking you some questions. And my first question is the number 3,456 divisible by 9?
7, 13, 18.
Let me write that in a better way. Is it true that 9 can divide 3, 4, 5, 6? So I'm using the symbol here, divides. 9 divides 3, 4, 5, 6. True or false?
I'm going to say true.
You're going to say true. And how do you know it's true?
I know because this is a division trick that we teach the year 7s.
Oh, yeah.
Yeah, so sum the digits. 3 add 4 add 5 add 6 is roughly 18. And then 18 is in the 9 times table. 1 add 8.
And I know that because 1 plus 8 is equal to 9.
Yeah, and that gives us a number in them. And if that's true, that's our divisibility test.
That is perfect. And I'm so glad that you guys both came to class knowing that fact, because for the rest of my fact, I'm going to be asking you something very similar. So here's my next question. Does 15 divide 195? True or false? And Joe, I've asked you enough difficult questions already today, so I'll help you out. 1 plus 9 plus 5 is equal to 15. Yes, it does. Are you happy with that?
Not entirely.
Okay. I thought I had your trust, but we can do this if you like.
Yeah.
I'm happy with your result.
True.
So 10 times 15 is 150 plus 45. Yeah, I think that's valid. Yeah. Okay, try another one then. Try another one if you don't like that. What about 285? Can I divide that by 15? Let's just check. 2 plus 8 plus 5 is 15. Yes, I can. Yes, 285 does divide by 15.
Mm-hmm.
I challenge you to tell me I'm wrong. It definitely does divide by 15. Maybe I could do another one. Is it true that 15 divides 375? 3 plus 7 plus 5. Wouldn't you know, that's equal to 15 as well. I think I'm onto a winner here. So can you notice why this is working? You mentioned before we had this division trick for 9, and it actually does link back to modular arithmetic. You'll notice that 9 is one less than the base that we're dealing in, base 10, and therefore if you do the algebra, you'll notice that the sums of digits should work out. But 15 is completely unrelated to base 10. So why is this happening?
Is it just a coincidence, Ben, that you've chosen numbers that are you've chosen those numbers deliberately because it's a coincidence, you know? Is that what you're getting at, or?
I mean, my notes only had these 3 examples, but if you want me to flex a little bit, I could come up with another one on the spot. So I could say 6, 4, 5 would also divide by 15. So it's not a coincidence per se, but it is curated. That's probably a good word to use.
I feel like because even if you switch them around, so you've got like 195. If you do 915, that also works.
It does indeed, and you're getting closer to the trick here. I'll give you another one, Paddy. See if you can figure this one out. 15 will divide by 3, 3, 3, 3, 3, 3, 5.
Okay.
And I know that's going to be hang on, with a 1 at the start, and I know that's going to work.
Okay.
Okay, right. So we mentioned the division trick of 9. If you add all the digits together and it's a multiple of 9, the original must also be a multiple of 9. There's a very similar trick that works with the number 3. If you add all the digits together and that's a multiple of 3, then you know your result is a multiple of 3. And as it so happens, I was choosing those numbers.
Yeah, you need a number that's a multiple of 3 and a multiple of 5.
And there's a great division trick for multiples of 5. It's got to end in a 5.
Yeah.
So this was a sneaky one on my part, and I know that if it's a multiple of 3 and 5, it's a multiple of 50. So that's quite nice. Okay, see if you can work out what's going on with this one next then. So for my next number, I'm going to go for 133, and I would like you to tell me whether you think it's divisible by 7.
Oh, I hate divisible by 7. It's
okay.
I've seen some really grim algorithms for it. Yeah,
I've got a great algorithm for you.
According to one of my year 7s earlier this year, nothing is divisible by 7.
Yeah, sounds about right.
Well, that's because everything's a multiple of 4.
By 4. Yeah. We've been through this. Yeah.
So we know that 133 divides 7 because of course 1 plus 3 plus 3 is equal to 7.
No.
Of course, and I know that you're not believing me, but of course, as we all know, 7 times 19 is 133. That's no problems there, right?
Right, so, none. Perfect.
So, Katie called me on my BS earlier on when it is just coincidence, isn't it? So the 15s, I had a sneaky trick, but this 7 one I think is quite fun. It is a coincidence that 1 plus 3 plus 3 is equal to 7. Do you know why we know that's a coincidence?
If you try it for 140, it doesn't work quite so well.
It won't. No, you're absolutely right. So you can find counterexamples. If anything, the counterexamples are easier to find than the examples. But I would argue it's a coincidence because 133 is a quantity. I can have this many watermelons in my kitchen, fine. But the digits 133 are base dependent. They work on base 10. And there was a nice connection for the trick with 9 that it related to the base 10 because it's always 1 less than. But that trick goes out the window with the base 10 and the number 7. Curiously, you can use that same trick when converting into octal. So if I were to write the number 133 in octal, I could check that it's divisible by 7 with the same digit sum trick, because that's then 1 less than the base system. But otherwise, it's a coincidence. And whenever we have coincidences in maths, we like to give it names. And this one was named by an Indian mathematician, and he gave it the name Harshad, which is beautiful. It actually means the giver of joy in Sanskrit. And why? Because these numbers give us joy. So this is a subset of numbers that I'd like to talk to you today about, which are numbers whose digit sums add up to the number that divides the original. So let's talk about the divisibility with different base systems. If we go back to the one that we met earlier, 195, we said this was divisible by 15. Of course, 195 in base 10 is the digits 195. But if I write it in base 8, my favorite base system is octal, then we have 366, which is in base 8. For those of you who are less confident, this means there are 3 lots of 8 squared, plus 6 lots of 8 to the power of 1, plus 6 lots of 8 to the power of 0. So that's how the number is constructed. And we know that this must be divisible by 15 because it's the same quantity as 195, the same number of watermelons. But what do you notice here?
It adds to the digits
Yeah,
up to 15.
It still adds up to 15. And again, this time we're talking about the quantity 15 rather than the digits 1, 5. We do have to be careful with this one. But what this means is that the number 195 is 10 Harshad. So it is a Harshad number in base 10, but it is also 8 Harshad. It is a Harshad number in base 8. So we've got this lovely property, that this extra joy that has been brought to us of numbers that are in multiple base systems.
Yeah, this is now making me wonder what's the most bases something can be Harshad in at the same time.
Well, I'm going to go in a different direction first. Would you like to know, can I ask you to guess how many runs do you think there are of 20 consecutive numbers that are all Harshad numbers, all 10 Harshad numbers? All in base 10, 20 consecutive numbers.
Okay.
One?
I don't know. Is it 4?
So there are an infinite number of consecutive runs of 20 quantities that, when written in base 10, are all Harshads.
Incredible.
Incredible. The smallest one, by the way, has 44 billion digits. Over 44 billion digits.
Right.
So they're big numbers. Would you like to know how many runs there are of 21 consecutive quantities?
0.
Yes, please.
0. Yeah, absolutely. Because we like to jump straight from infinity to 0.
Yeah, love it.
Excellent. So these are the Harshads. There does not exist a run of 21 numbers. In fact, would you like a cheeky Shakespearean fact for number theory on Harshads?
Yeah.
Okay, so if you can guess the answer. What is the largest number of runs of a B Harshad number?
2B, or possibly not.
Oh, you're close. It's 2B, but not 2B plus 1. So for any base system, you can double that number of the base system and find a consecutive run of this many Harshad numbers in that base. But that's the limit.
So in base 10, you can have 20, but not 21. Yeah.
Exactly right. Exactly right. Yeah. So this is this is a beautiful fact, and I think it brings me joy. Still haven't mentioned the number 4. So let's do another quick fact that will cue you in for the challenge round. I think it is going to be fairly obvious that all of the values from 0 up to n inclusive are n Harshad or higher. Does that make sense? So either n or more than n in the Harshad quantity. So for instance, number 7 is definitely 8 Harshad.
Because the sum of its digits is divisible by
7.
7.
Because how do you write 7 in base 8? Well, 7 in base 8 looks like that. 7 in base 9 looks like that. In fact, for any base 7 or higher, the number, sorry, I should say n minus 1, shouldn't I? Because the number 7 in base, oh no, it does work. So the number 7 in base 8 or base 9 or base 10 all looks identical. If you consider 7 base 7, though, how would you write the number 7 in base 7?
1, 0.
Indeed it is, yeah, 1, 0 in base 7, but check the digits. 1 plus 0 is equal to 1, and 1 divides 7. There we go. I suppose when talking about positive cases, it's always helpful to check if all cases are true. So should we just have a quick look at 7 written in a lower base system? And I've not tested this, so let's see if we can do it on the fly. How would you write 7 in base 4? That's certainly not how you'd denote it.
It's 1, 4, and 3 1s.
So that would be 1, 3
yeah.
in base 4. And let's just check to see if this works. Is 1 plus 3 a number that divides 7? No, it's not. and seven's conveniently prime, so I could tell in advance it wasn't going to work. There we go. So we know that 7 is Harshad in base 7, 8, 9, 10 and above, but actually it's not going to be Harshad in any base below. So, Katie, I think you had an interesting question earlier, which is what's the number that has the most base Harshads? Is that right?
Yes.
Well, I'm going to answer that and say that some numbers are what we might call all Harshad numbers.
Right.
Would you like to take a guess as to how many numbers are all Harshad numbers?
I mean, we've been guessing 4 for everything because that's the number of the episode, and
So,
it feels like this is the moment where it's going to come in, right?
Indeed. I'm going to abuse notation here and say the size of the set of all Harshad numbers is indeed 4. There are only 4 of them. I'm going to give you
perfectly reasonable notation. I don't know what you're talking about.
I am going to give you.
You put some quotes around it. It's perfect.
Obviously, the bracket notation as well, just to be certain. There are 4. I'm going to give you. I'm going to give you 2 of them that are pretty obvious. So I think we can all agree that 1 is going to be Harshad in everything, because and also 2 is Harshad in everything because of the property that it is a Harshad in any base itself or higher. Obviously, we're not going to count unary because that's ridiculous. So the first base system we can really play with is binary. Those 2 are both going to be golden.
I love unary. Like, if anyone's not encountered unary, it's base 1, and you just write 1 the number of times that the number is. Right, it's just a whole bunch of 1s. So however many 1s are, the number is that many. Yeah.
Well, I like to think about unary being the quantity rather than the representation. So I think of unary being measured in watermelons, and it's because you get those textbooks from the olden days where it's always Simon has 43 watermelons that he's carried home from the shops for some reason.
Yeah.
I'm going to give you another one that is a little bit harder to show, but it's going to help you with the challenge round, and that is 6 is also an all Harshad number. So should we just check 6 briefly? So in base 6 or greater, it's going to be obvious because of the rule we described earlier. So we only really need to check it in the bases lower than 6. So when written in base 2, it is 1, 1, 0, and 1 plus 1 plus 0 is 2. 2 divided 6, perfect. In base 3, it is 2, 0, and 2 plus 0 is 2, divide 6, perfect. In base 4, this one's a bit cheeky, it is 1, 2, it's written in base 4, 1 plus 2 is 3, 3 divided 6, and of course in base 5, we've got another number that is just 2, so that is 1, 1, written in base 5, that also works. Okay, so 6 is golden. There's only 1 more to get. And I'm going to let you decide which of the 3 following options you think is the most likely culprit for the 4th all Harshad number. Grab a pen, grab some paper, because I'm going to get you guys to figure this out for yourselves. Is the only remaining all Harshad number 3, 4, or 5?
Okay, none of those are what I was thinking.
Okay. Yeah, I was expecting like 40,500,000,000. No.
Yeah, I was hoping for 28.
It's not 3.
Definitely not 3. What example have you got for 3?
In base 2.
The only base that's appropriate.
1, 1.
And 1 plus 1 does not divide by 3.
Not a factor of 3.
Yeah, you might notice 3 is a prime number.
Ooh, 4. I reckon it's 4.
Well, let's just check 5, shall we?
Yeah.
So,
all right.
So how would you write 5 in a different base system?
Quick at this.
In base 2, it's 1, 0, 1.
It is indeed.
Which is 2. Yeah.
Yeah, and hey, look, 5 is a prime number. So 4 is going to be the only other all Harshad number, and we can check some of the values. So we got 1, 0, 0 in base 2, or we have 1, 1 in base 3, and actually that's all we need to check because we don't need to check 4 or above, but both of those work. 4 is all Harshad. I don't have the proof that there are no other numbers greater than 6. That is an exercise for the viewers to do in the comment box below.
Just stick it in the comments,
yeah. Once you find it, pop it down there. It's just next to the like and subscribe button. You won't miss it. But that's my fact. There are only 4 numbers that are divisible by all of the digit sums of any base system, and one of those is indeed the number 4.
That's a really cool fact.
Super fun.
Did it bring you joy?
Yes.
Then its name is appropriate. So that brings us on to the next part of our chat show where we talk about an integer sequence. And this time it's brought to you by Paddy. Paddy, what have you got for us today?
I brought the comma sequence, which is the set of numbers that you can see there. It's easiest if you demonstrate this, actually. So if we have 1 and then 12 and then 35, which are the first three numbers in the sequence, we can see that the difference between them is here it's 11 and here it's 23. And the sequence is made by adding the numbers each side of the comma to the previous term. That's how we get it. So
hang on. How do you know what the second digit is going to be if you haven't?
So there are sometimes going to be two options,
right?
And under this, you have to always choose the lowest possible option.
Right. Okay.
So if
Is that what you mean by the earliest?
Yeah, the earliest is the first one that it can come up with. Okay, so for the next number, we're going to add 50 something to it.
Yeah.
So that's going to give us an 8 as our first digit here. So we must be adding 58 to this to get our next value.
But if you add 58 to that, you'd get 93.
So that doesn't work, does it?
Well, if it's not 8, it's got to be 9.
Yep. So we add 59, we get 94. Okay. So for the next number, we're going to add 40, which is get us to 130 something. So adding 41, that's 135. And this sequence carries on in that way.
So can we see if we can work out what this missing one here is?
Okay, so it's 248. So the first digit's 8.
Yeah.
Because it's always going to be a two-digit number we're adding.
Is it definitely not going to be 48?
It's definitely going to be 8. It's always the
So
number.
it's just a single digit.
Yeah.
Okay.
Just a single digit. So the highest you can add is 99.
So 248 plus 80 is 328.
Mm-hmm. So
that doesn't begin with a 0. Plus 81 would give us...
Well, surely we know it's got to be 83 then.
It's got to be 83, yeah, that's it, yeah. So 83, and that gives us 331.
Yeah, it does.
Yeah.
And that is the next number in the sequence there.
This is ridiculous, and I love it.
Oh, and that's why the next sequence doesn't jump by very much.
Yeah,
because that's now only gone up by 13.
Yeah, because the difference between is just created there.
So this is not a sort of stable function. It doesn't increase or decrease by an increasing or decreasing amount.
Nope. It's an entirely random amount each time. It just varies hugely.
Well, it varies between 10 and 99, right?
Yeah.
It's always a two-digit number that it increases by.
But you don't know if it's increasing. Sorry, I don't know if it's going to go up by more or less than the time before. It's going kind of very variably. What would happen if we started, instead of starting with 1, what are the next numbers if we start with 2 instead?
Okay.
So if we start with 2, we add 20 something.
Mm-hmm.
So we get a number that's also in the 20s potentially.
Whilst you're doing 2, I'm going to try 3
if we
by
added
myself.
22, we'd get 24.
Yeah.
And that works.
That does.
And then for the next one, we'd add 40 something. So we'd get a number that's potentially in the 60s. In order to get that, we'd have to add 42, which doesn't work because that doesn't end in a 6. If we added 46, we'd get 70. So that doesn't work. So if we put a 7 at the start of the next number instead and tried adding 47, we'd get 71.
Which is the next value.
Yeah.
And then
I think I've got it. Like it almost always, like often it will be the same digit as what you'd get if you just added that number of tens. But sometimes that makes it slightly too big, so you have to go up 1 from that.
Yeah, exactly. Yeah. And
hang on, I think I found one that's terminated almost immediately then.
So you're going to go to 6. If you add 6 to that, you're going to get 90 something.
Yeah.
And adding 69 to 36
puts you over 100.
Yeah. So.
Oh, but I can't. Yes, I can go down again, can't I? I can say 61.
Yeah.
You
And then
can't.
you
No, I
no, but that
can't.
doesn't.
That wouldn't
That's
fulfill.
97.
Yeah, you've broken it.
So can I do
have broken
60?
Can't do it.
No, I don't think it can't be broken. It's got to be 64.
You can
Well,
put
if
60. You
you're
can
No,
put
hang on.
61.
It's got to
If you
be a
put
1,
61,
surely.
that would only give you 97, which is wrong because
So
the
it can
one.
only be a 1 or a 9, is what we're saying, isn't it?
yeah.
Yeah,
I think
you've
it's
broken it.
because you know that the number you're adding starts with a 6. And from 36 you can add 60, 61 all the way up to 69, but none of them happen to line up with the right first digit for the next one.
That's
So
it.
you're
Yeah.
telling me that the sequence for starting with a 3 has 2 terms?
Yeah.
Yes.
Possibly the shortest sequence in the online encyclopedia of integer sequences.
If it's in there, yeah.
If it's in
The
there.
sequence starting with 1 is in there.
How much
and
did you say starting with 1 has?
Over 2 million, and starting with 2 has over 4 million.
And it goes up to there, doesn't it? Oh, that's a lot of 9s.
Yes.
I'm sad that I picked a duff one.
I don't think you picked the duff one. I think you picked a really interesting one.
Okay.
Because it proves
fun
that
to
they
see
terminate.
it terminate. Yeah.
Oh gosh.
Yeah.
Anyway, yeah, that's really fun, and I really enjoyed that.
Yeah.
Yeah.
That's such a great sequence.
I noticed it doesn't satisfy Benford's law. Nice.
Cool.
Oh, well, thank you very much. So I think it's time for us to start wrapping up for the evening. So let's talk about plugs and links. Paddy, what would you like to plug today?
I do not need to plug anything except, no, I don't need to plug anything. You could direct people to my film podcast if they are needing some help sleeping, with Invasion of the Poddy Snatchers.
On all major platforms, I'm sure.
Yes.
Amazing.
Yes,
Yeah.
fantastic. Or I think you've got a social media account.
Yeah, at Paddy Maths on pretty much everything.
Fantastic. And Katie, what would you like to talk about?
Well, I brought along finite groups here as a thing to talk about, and the finite group, which I have pasted in the gigantic monster logo of. This is the maths, I guess, hangout that I run with a few other people. So we have a Discord kind of chat, and we have a little community of people who join that. We also do monthly live streams, which are kind of a lot like this, where we just kind of amble around a nice, interesting piece of maths for an hour or so and get slightly confused and then get back on track. And there's if you join for free, you can join the Discord and kind of share maths memes and talk to all of us about different things. If you want to watch the live streams or the recordings of the live streams, you can join as a paid member through Patreon, and it's like £4 a month, or you can pay for individual recordings to watch them back. So if anyone is interested in hanging out with cool maths people in the Discord, you'd be very welcome to join us.
Fabulous. And again, links in the description.
For me, you can find me on Blue Sky. I'm at mathematicians-pod, and that is because I run a podcast about mathematicians. That is the history of the mathematicians that wrote the mathematics. So if you want to know more about ancient mathematicians, you can find me on all major platforms. And of course, we should say the other big plug, the reason why we're putting this group on is to get more people talking about maths out loud in a public forum. So if you are sitting there thinking that I too would like to talk about maths out loud with some other people, then come and join us and be on a future episode. If you've got a favorite number that you want to chat about, links in the description below, and you can be on a future episode.
Yeah, if you could do so as coherently or more coherently than we have just successfully done, then you would be very welcome.
Excellent. Until next time, it's bye from me.
And bye.
Goodbye.